Okay, hello. So we just left class, and here's what I wanted you to see. We left with this goal, okay? And just to orient you here, the X and Y axes, this is the X axis right here, okay? This is the Y axis. You can just ignore this axis. This is a Z axis, but all it's trying to show you for right now is just the fact that it's trying to show you that this solid is actually coming off of the paper, okay? So here is the curve right down here. That's y equals root x. So this curve right here is y equals root x. And this was what we had this was our task. We were trying to shape kind of a solid where the area of the base, and I think I said to go from 0 to 10. So I'm just going to go down here and let's just ignore this for a second. Let's just say I'm going to x equals 10, I think is what the objective was. What you had was some situation like this. I said, take a look at y equals root x, the area bounded by y equals root x, and the line x equals 10. This area right in here is the base of a solid, and it's the base of a solid whose cross sections perpendicular to the x-axis are squares. And so what you were doing in class with some success and some, let's admit it, Oliver, some Play-Doh disasters, you were getting there. You were getting to shaping this thing where the squares are popping out, right? They're coming off of paper. But notice here, the largest square is at x equals 10, because if you think about it, x equals 10, this side is largest. So the square coming off of the paper is going to be the largest at x equals 10. And then look what happens to the squares as you head towards 0. See how the height of this square right here is shorter, because if I move down, right, x is diminishing and the squares coming up off the paper are getting smaller and smaller. And eventually we're down here, right, where the solid comes down to a point. And so I'm going to attempt to draw this square up here, right? See how it's like an atrocious attempt to draw a square here? That's a square cross section. There's another square cross section right here coming off of the paper. Oh, how ugly. Ugh, yuck, 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 yuck. Okay? But the point is here, we've got squares coming off of the paper. Let me try and draw it again. Let's see if I can do an even better job. That's not too bad. And that's not too bad. That's not too bad. That's not too bad at all. Yeah, okay, there we go. I can kind of see that. That's actually not bad at all. I kind of like that. So this solid looks like this, right? And you can think of it as these squares coming off the paper. And now, once again, I said to you in class that the calculus, the math of this is actually very easy. If I want to describe this solid, the volume of the solid, again, we're talking about the volume of the solid, it's going to be a definite integral. Let's talk about the dummy first. How are these cross sections stacked? They are stacked over an interval of x, dx. Okay, what is the interval of x over which they are stacked? They are stacked from the interval 0 to 10. Now, you know what the integrand is. The integrand for all of these questions, the integrand has described the area of one of those cross sections. In this case, the cross section is a square. Well, let's take a look. If we look at the area of one of these cross sections, the area in general of a square is side squared. It is side squared. Everyone okay? But if you think about this, the side is just this distance from the x-axis up to root x. And the side of a square here is equal to root x. That means a side squared is root x. That's that side squared dx, which of course we could simplify to the definite integral 0 to 10 of x dx. That is the volume of that solid. Okay, let's do another one. Let's do this. Let's say I have the same base area. The base area is here. Let's say y equal root x. The base area is bounded by y equals root x and x equals 10. And this is the base area right in here, like it has been before. This is the base area. All right. And now I'm going to tell you this. This area is the base of a solid whose, I'll write this down, cross sections, now I'm going to write down cross sections perpendicular to the y-axis are semicircles. Oops, semicircles. Okay, this question here, and this is Mateo, he wanted me to write this down. In this case, we had a solid whose base area is the fluorescent green. In this case, we had cross sections perpendicular to the x-axis, and those cross-sectional shapes were squares. Now, not only am I changing the cross-sectional shape, I'm changing the orientation. And again, I'm going to do my very best. I'm going to draw a few cross-sections. And again, we're going to have to be a little bit, don't be so judgmental about ourselves. So the cross-sections are stacked perpendicular to the y-axis. And these are semicircles, so they kind of come up like this, right? They come up like this. They come up like this. I'm going to draw a few semicircles. All right, and so the area here, okay, so here is one cross-section right here, and then another cross-section. Let's see if I can keep this all straight. And then here is another cross-section. And let's describe this volume. Well, let's do it together. One more time. The first thing you look for is how are the cross-sections stacked? How are they being added up? They are being added up over an interval of y. What is that interval of y? Well, let's see. 0, and then let's see, what is this interval of y? Well, when x equals 10, the upper limit is root 10. That's the y coordinate of this point. Now, once again, that integrand is always going to be the area of one cross-section. Well, let's see. The area of one cross-section is this. It's a semicircle. And what I like to do is this. I like to kind of think about it this way. The area of a semicircle in general is 1/2 of pi r squared. Right? And if we build it like this gradually, we really avoid the possibility of making any careless mistakes. That's the area of a semicircle. Now what I'm going to do is I'm going to go to my region here. I'm going to draw that critical body part that I need, and that critical body part that I need is the radius. And if I look at this here, the radius, where do we draw it, everyone? We draw it to the curve. This is the radius. This is the radius right there. Well, let's see. Let's see what's going on. The radius, right? We know the radius here equals 1/2 of the distance between this curve and this curve. Agreed? The radius is 1/2 of the distance between this curve and this curve. And Nicole, this is for you. How do I find the total distance between the two black curves, which happens to be the diameter of these semicircles, right? The distance is upper curve minus lower curve. But in the horizontal orientation, right curve minus left curve. Let's see, this is the same thing as x equals y squared. The distance between this curve and this curve is 10 minus y squared. Half of that distance equals the radius. So in this particular picture, the area of that semicircle is 1/2 pi, here's the radius. 1/2 10 minus y squared squared. You have to keep track of exactly what's going on, right? So this is just the general area of a semicircle. Here, I'm figuring out what the exact actual radius is. And this, by the way, is going to equal my integrand. I'm pulling the 1/2 out. This is 1/4, 1/8. This becomes pi over 8 is the constant pulled through. This becomes 10 minus y squared squared dy. Okay? These are all these questions. Notice, and this is Arjun's point, notice in these questions, there's no axis of revolution. There is no axis of revolution. There's no revolving at all. What we do have is the constant idea of adding up cross-sectional areas stacked over some interval. And again, the constant is the integrand being the area of one of those cross-sections. Okay, let's do one more. All right, what you've got here are the curves y equals x and y equals x squared. And the area between the two represents the base of a solid. It's the base of a solid, everyone, okay? That is the base of a solid where the cross sections, so the cross sections perpendicular to the y-axis are rectangles, okay, where the height of each rectangle equals double the width. And when we talk about the cross sections that are rectangles here, let's call the height of each rectangle, we'll call height like the distance the solid comes up off the paper. So let's take a look at this wording again. The cross sections perpendicular to the y-axis are rectangles where the height of each rectangle is double the width. Go ahead and try it on your own and then replay me to get the answer for what the volume integral expression would be. I'm going to start working on it right now. Okay, well, what I'm going to try and do, as I always do, is I just say to myself, okay, I have cross sections perpendicular to the y-axis. So I know I'm slicing this way. Okay, and what this is telling me here is my cross sections are rectangles such as the height that it comes off my paper is double the width. So that means each of these, I'm going to do my best here, it comes up this high. That's not too atrocious, I don't think, right? I'm going to come up this high. Okay, it's not, well, actually this is pretty bad. Well, oh well. What can Yam do? Okay, so I'm going to talk to myself about, well, how can I describe the area of one of these cross sections? This is the width, and the height here is double the width, so it's 2w, okay? And I'm talking to myself here, the area of a rectangle in general is length times height, or in this case, I think I called it height times width, right? And in this case, the area of each cross-section is going to be 2w times w, or just 2w squared. But in this case, w is the horizontal distance between this upper curve and this lower curve. So I know that the width, this distance here, w equals y minus root y, right? So if w equals y minus root y, then the area of one of those cross sections is 2y minus root y squared. And I should say this, I'm noticing the cross sections are stacked over an interval of y. My integral is going to be in terms of y. The interval of y is 0 to 1. And here is my integrand. 2 times y minus root y squared equals this volume. Okay, that hopefully should be really nice and clear. Really fun class today, and I have to say, just really, really proud of the work you're doing, everyone. You're doing a great job. Homework is posted on the teacher page, I think probably right above or below this screencast. Okay, goodbye.